Oscillations Lab. The purpose of this lab is to analyze how the characteristics of a spring affect the motion of an object that hangs from it. The fundamental concepts that we are going to use are non-constant forces, specifically for spring force, gravitational force, conservation of energy, and the momentum principle, as always. Position data is tracked in Tracker, and it looks as follows. You can see that the object moves both in the x and the y, and we have our x plane as this, and vertically is our y plane. This is the x position of the mass over time, and this is the y position. As you can see, it oscillates between close to zero or not close to zero. It oscillates between a negative value and a more negative value, and the x position oscillates between a positive value and a negative value. So we can use these points to find the period of this oscillation. I used the x position because it was a little cleaner, and I used the lowest point, change in time between the first four lowest points, to find the average value of the time period of the oscillation, and I plugged it into this formula to find the spring constant. And then I used the spring constant, plugged it into the spring force formula, set it equal to mg to find the rest length of the spring. And then we have a diagram of the spring captured amidst its motion here. And we have that L is equal to where the ball is minus the origin, which is where we have the spring attached to a fixed point. We have that L hat is the vector that points in the direction of where the ball is relative to the origin, and S is the magnitude of L minus L naught, which is just how much the spring is stretched. Spring force and gravitational force are the two forces that we have coded. We have that mg points downwards, and that spring force opposes L hat because the spring is stretched. We also have that spring and gravity are the only exerted forces, so we can account for F net only through only F grav and F spring. And then we also have the good old momentum principle, which we can also use to derive the velocity, the definition of velocity. Here we have the observed data versus the predicted data. Observed data is in red, collected from Tracker, and in blue is the predicted data computed with ClosScript. As you can see, the predicted data is a little smoother because we have a smaller time step. In the y position, the y axis, they are a little more closely aligned than they are on the x. However, they are still reasonably within sync of each other. We have the energy principle written out in code here. Kinetic energy, gravitational potential energy, spring potential energy, and total energy are given by these equations, and all of them are combined to have the total energy. Now we know that the change in total energy denotes how energy changes forms as the ball moved through time. We also know that the change in total energy is zero because energy isn't added or removed from the system during the length at which we observe it. So the change in energy versus time look as follows. We have small changes in kinetic energy as the mass is accelerated back and forth, but our potential energy changes are much larger in magnitude. We can also see that the spring potential energy changes has lower troughs than the gravitational potential energy change, and this shows how the spring potential energy has more influence on the object at certain times than the gravitational potential energy. And the reason the gravitational potential energy changes is because spring affects how the mass moves. Now, satisfying the energy principle, we know that energy is neither created nor destroyed, but it can be converted into different forms, which include kinetic, gravitational potential, and spring potential energies. And when it's a closed system, there is no change in total energy, which is what our system we observed is. When it's an open system, energy is added to or taken from the system, which has not taken place here. It did take place right before we let it go. When the hand took the mass and raised it higher up, that was adding that was adding gravitational potential energy to the system. But when it let go, there was no more gravitational potential or spring potential energy added to the system. Now the oscillation periods are found by taking the times of the lowest periodic x and y values, taking the difference between these times individually, so this is the difference between this, and so on, and then averaging these three gives us a period, and same with the y value. That concludes my TED Talk. Thank you for attending.